Alright, ladies and gentlemen, so today we're going to take a look at how we can analyze our functions a little bit more, and we're going to be looking at something called average rate of change. And what average rate of change is it's the difference in the outputs divided by difference in input. So you're looking at how fast it's changing over input. Sorry. You're looking at how fast it's changing between two different points is really what it's doing. So we're going to kind of work through a couple of examples here. So Max and his younger sister Evie are having a race in the backyard. Max gives his sister a head start and they run for 20 seconds. The distance they are along the race in feet is given below, with Max's distance given by the function m and Evie's is the function e. Okay, how do you interpret the fact that m of 12 equals 30? Well, this is our input, which is our x. Here are your x. So that's telling me then that after 12 seconds, right, Max, because we're talking about the m function, has run 30 feet, right, because here's your output. So 10, 11, 12, nope, these are going by twos, 10, 12, so we're talking about this point right here. So after 12 seconds, he's run 30 feet. Okay, if both runners start at time equals 0, how much of a head start does Max give his little sister? So here's Max, he's starting at 0 feet, right? But here's his sister. His sister is starting at 25 feet. So he gave her a 25-foot head start. Very nice of him. How far does Max run during the 20-second race? Well, that's going to be my n for my m function. Here's 20 seconds. All right, so he's run 50 feet. So Max is 50. Evie, right? Evie ran a little bit further because she did have a head start. Evie ran 60. All right, does Max catch up with his sister? No. How do I tell? The graphs don't intersect. All right, what calculation can you do to find Evie's distance? Well, oops, sorry. Well, so, to see how far she ran total, sorry. So you can do, right, she ran 60, but she had a 25-foot head start. So she really ran 35 feet in the same amount of time. All right, let's see what's next. So how fast do Evie and Max travel? In other words, how many feet do each of them run per second? All right, well, our formula, this goes back to chapter 1, distance equals rate times time, right? And we know that for Max, he ran 50 in 20 seconds. So I have to divide both sides by 20. So that means he ran 2.5 feet per second. Evie, we're going to use the 35 because she had the head start. So she ran 35 feet. I'm going to start with the same thing here. 35 feet in her 20 seconds. So again, I have to divide both sides by 20. So that's giving me 1.75 feet per second. So we know that based on this graph, that Max ran faster, but because he gave Evie a head start, he never caught up with her. Okay, in the first exercise, we were calculating the rate that the function's output values were changing compared to the function's input values. This is known as the average rate of change. All right, this is also called, which we did a little bit last year, this is also called the slope of a line. All right, slope of a line. So, our formula, which I did talk about a little bit before. So our formula to finding the slope of a line, right? This looks pretty, right? It's a little bit weird here. So it's f of b minus f of a over b minus a. how much the y values have changed divided by how much the x values have changed. Remember, y values are your outputs and x values are your inputs. So we did kind of put that up there. But let's see how this is going to work. So consider the function f of x equals x squared plus 3. Find its average rate of change from x equals -1 to x equals 3. So the first thing I have to do is I have to evaluate those functions. So I'm going to do f of -1 first. So it's going to be -1 squared plus 3. We know that -1 squared is 1, plus 3 is 4. So this was your in, this is your out. All right, then I'm going to do f of 3. So that's going to be 3 squared plus 3. 3 squared is 9, 9 plus 3 is, oops, getting a little too far ahead of myself. 9 plus 3 is 12. So to find my average rate of change, right, here's your out, here's your in. So I'm going to take and subtract these numbers, 12 minus 4, divided by the input numbers that got those. So divided by 3 minus -1. So 12 minus 4 is 8. 3 minus a -1 is 4. So my average rate of change is 2. So you're evaluating the functions both and then going through and doing your subtraction. So let's see, what else do we have? The function h of x is given in the table below. Which of the following gives its average rate of change from 2 to 6? So I don't care about this one, right? I just want to go from 2 to 6. So there are my x's, there are the y values I'm going to use. So I'm going to do 9 minus 3. Since I did the 9 first, I have to do the 2 first. So 2 minus 6. All right, well, 9 minus 3 is 6. 2 minus 6 is -4. And then this would reduce to 3/2, and you can put the negative sign out front. So that would be choice A. All right, next one. Frances is selling glasses of lemonade. The function g of t equals models the number of glasses she has sold. What is the average rate? So we're going to do, we have to evaluate for t of 2 and t of 6. All right, so I'm going to do g of 2. So that's going to be 2 squared plus 4 divided by 2. 2 squared is 4. 4 plus 4 is 8. 8 divided by 2 is 4. Now I have to do the same thing for 6. So g of 6 is going to be 6 squared plus 4 divided by 2. So 36 plus 4 divided by 2, that's 40 divided by 2, so that's 20. So now that I have my numbers, now I have to set up and do my subtracting. So we're going to have 20 minus 4, those are my outputs, divided by the inputs, 6 minus 2. So 20 minus 4 is 16, 6 minus 2 is 4, so 14. Now it told me to use the correct units or label in my answer. So we're talking about, this is the number of glasses sold after t hours. So glasses per hour. Sorry, I ran out of room there. Okay, so just doing a little bit different with our functions, being able to evaluate them, and then do some subtracting. So, any questions? Bring them to class. Otherwise, have a good night.